Okay. So greetings, computational neuroscientists. For the next little while, Fred and I are going to take you back in time to a similar situation as Christopher Columbus. Now, I'm not saying we're going to rediscover America, and I'm not claiming that he was the first to say that the world was round, but we're going to go through a similar debate, where the Spanish masses thought that the world was flat, and Columbus argued that the world was round. In the same way, we're going to tell you that statistics should sometimes be round. So, in the case today of our debate, you will be the Spanish masses, and Fred and I will be your Columbus. So, we're going to try to convince you that normal statistics is not always the way to go. Sorry, Kelly. But rather, sometimes, depending on the type of data you're working with, you have to look at different alternatives to linear statistics, because the linear statistics significance that you get may not always actually be significant. So as I said before, the type of data that you use should determine what kind of statistics you should use. So circular statistics should be used whenever you have a vector data set. So a vector data set is a data set that has angles in association with angles. And what this means is that there's no true zero. So you go from 0 to 360 degrees, where 0 and 360 are the same. There's no true zero. And if you have a range from lower to higher, there's none. There's no lower or higher value. It's arbitrary. So rather, vector data has a periodicity. So if you were to think about it in terms of the hours in a day, you go from midnight to 1 in the morning, to 5 in the afternoon, to 7, to 11, back to midnight, where 3 o'clock is not less than 5 o'clock. It's just a different time than 5 o'clock. If you go to months in a year, you have January, February, all the way to August, December, and then back to January. Again, bam, you go back to where you started. Nothing less, nothing more. And something more relevant to us when we talk about neuron tuning, if you talk about empty neurons and their direction tuning, you have from 0 to 360 or 359, the specific tuning of a neuron. And you can go, and then again, as I said before, 0 and 360 mean the same thing. So there's no true zero. It wraps around. Now, we're normally used to talking about angles in terms of degrees. But for circular statistics, what we normally actually use is radians. And you can express anything in radians using this equation, where x is the data point that you're looking at, and k is the number of steps that x is measured in. So if I take x over k, this tells me the proportion of the circle that your data point represents. And that's why you multiply it by 2 pi, which is the circumference of the circle. So when we talk about degrees, your k is 360 degrees, and x is the angle that you want. And you can easily go from, well, not really easily, you have to first perform this calculation, but you can go from radians to degrees and from degrees to radians using this. So let's jump into some of the statistics that we do, and let's find out why sometimes it's important to see the difference between linear statistics and circular statistics. So when we talk about calculating the mean, so I'm sure when Kelly gave her talk, that she said that the mean was just the average. So you add up all data points, and then you divide it by the number of sample points that you have in your data set. So here we have on the right a set of data points on the circular plot. If you were to take the linear mean of these data points, you would get the gray line, which is the linear mean. And you can see that that is not an accurate representation of the data set's mean. So instead, what you're supposed to do is you're supposed to take every single data set and cut it up into its unit or its components. So it's cos and sine, or x and y values respectively. Then you take the average of the cos, the average of the sine individually, and then you find the inverse tangent to get your mean. And you can see if you do that for this data set, you get the orange line, which is the correct representation of the data set here. And now I'll pass you to Columbus number 2.
We practice that. I mean, it looks easy, but hi. Similarly, the circular statistics framework proposed a method for the median. We'll see later why the median is so important. For now, we'll focus on its definition. Okay. The median is defined as a sample that lies the closest to the diameter that cuts the distribution into groups of equal dimensions, of equal number of samples. If the number of samples is even, The median will be in between two samples. If the number of samples is odd, then the median will be part of the sample set, that is, it will be equal to one of the samples. That's it for now. I'll be back in a bit with more about the median, and back to Nour.
It was important to switch. I don't know anything about the median. No. All right. So when we're talking about all these statistics, you can see that there's a lot of trigonometry involved, and sometimes when we talk about uniformly distributed circular data, it becomes very hard to describe a properly defined median. So thankfully, CircStat Toolbox has been created in MATLAB by a man named Philip Behrens from the Max Planck Institute in 2009. And it's just a great toolbox, very intuitive, that helps us to do these very error-prone calculations, and it helps to handle circular data properly. And you can download the toolbox from the website on the slide, which will become available to you after today's conference. Correct. All right. So we come back to radians. So radians is very important for the CircStat toolbox because everything you enter should be in radians. You could put in degrees, but you're going to get the wrong answer. So make sure that you put it in the form of radians. And with the CircStat toolbox, it's easy to do because you have this circ-ang to rad or circ-rad to ang functions, where you just have to input your angular data set, and then you get it. When we go to the mean, it's also very easy. You just have to use the function circ_mean, where alpha is your data, A is your data set of angles, and the W is the weighting for your data set if you're giving it binned data. And the output is the mean as well as the upper limit, the upper confidence interval, and the lower confidence interval, but the second two are only given if you give a second and third output argument. Should I take this one? Yeah, okay, I'll take this one. Cool, I got it. All right, so when you calculate the median with the CircStat toolbox, you can use the function circ_median with the same input of alpha, and it calculates the median for you, as simple as that. Now that we've talked about mean and median, there are many other descriptive statistics that this toolbox can do, including kurtosis and skewness and all that. But what's more important for our argument of why you should use circular statistics versus linear statistics comes when we're talking about inferential statistics. So, and before we jump into that, we're going to talk about an important assumption that we make with our data set. So when you do inferential statistics, and you have your data set, an assumption is normally made that your data set is coming from a normal distribution. That's the same in normal statistics, linear statistics, the same in circular statistics. But for circular statistics, that's a tongue twister. Circular statistics, the analog for normal distribution is the von Mises distribution. And you can see they're very much the same. They're described by the same parameters. They both have the mean, which is the location parameter, and they have the variance, which in the case for von Mises is the kappa, which are the shaping parameters. And you can see that from their equations, the big difference about how the distribution is shaped can be seen in where the variance and kappa are placed in terms of the exponential. For the normal distribution, you can see that the variance is within the denominator for the exponential, versus in the von Mises, the kappa is in the numerator for the exponential. So this affects how your distribution is shaped. So if I were to increase the variance or increase the kappa, you see that the normal distribution widens if you increase variance, and you have a sharpening or a narrowing of your distribution when your kappa increases. On the other hand, if you were to decrease the variance, you get a narrower distribution for the normal distribution, while you widen your von Mises distribution if you you decrease the kappa. My bad. So here we plot all three again when you have an increase of kappa or a decrease of kappa for the von Mises distributions. But we've replotted them in the rows plots below. The rows plots are a much better representation of circular data because it actually shows you how it wraps around and what portion of the circle your data actually takes up. Which is why from now on, every data that we're going to be showing you will be on rows plots. So what you can see very nicely, again, I'll repeat, is that you see how nicely the data is spread in the rows plot when you differ the kappa. So before we head into inferential statistics, we should talk about the metrics that describe this spread. And the most important is the resultant vector length. So when you calculate the mean for your data set, you are getting a vector. It's not just the angle that you're getting, but rather you have an associated length with it. And it's between 0 and 1. And the closer it is to 1, the more clustered your data is, and the closer to 0 that your data that the resultant vector length is, the more uniformly distributed your data sample is. Yes. Yes. So I'm not talking about the angle, just the length of it. Yeah, but no.
When you compute the mean, you sum up all the samples that you have, which are all vectors that could be, let's say they all have the same length. You sum them up, but necessarily, it's two way back, but necessarily that you're going to end up with both an angle and a length for the resulting vector. And things that, as we will see, we have some tests that are based on the length of the vector. If it is of a length of 1, the only way to get a mean vector of a length of 1, is that all your samples are aligned with the mean vector. As soon as you have some samples that are less clustered further away, it reduces to some extent, if you have like a perfectly uniform distribution, you will find a vector length of 0 because everything cancels out. So that's the idea. But this is the base for tests that are about to come.
Does that answer your question? Okay. All right. And you can calculate the resultant vector length using the CircStat toolbox, using the CircR, using the same inputs, which is your data set, and the weighting if you have bin data. Now, a lot of the time we're used to talking about spread. When we talk about spread in normal distributions, we're used to talking about variance. You can calculate a circular variance, but it does not mean the same thing. It is not the deviation from the mean. So you calculate it by just going 1 minus r, but again, it is not an actual representation of the spread like you are used to in normal distributions, which is why we always use resultant vector length when talking about the spread in circular statistics. And as Fred just pointed out, the R is what is important in being compared when doing the inferential statistics. The this is the resultant vector length. Is this? Yeah. Yeah.
The thing, we don't say it like very explicitly. The thing is that those measurements are, they do stats on these measurements for what is up to come. We have like a bunch of statistical tests that come from the circular distributions. And when you go into the math of those tests, you find that those are the metrics that are used on which they do statistics.
And you can also calculate C variance, the circular variance using the toolbox, circ_var with the same inputs as we talked about before. So here, once again, we have the 3 plots plotted with the different kappas. You see kappa 8, and you have the R equal to 0.9323. It's close to 1, which is very evident from the graph. Is more clustered around one area, as opposed to when you have a lower kappa of half, the R is 0.2650, which is closer to 0, which shows how it's more uniformly distributed as compared to when you have a higher kappa. Sounds good? All right, so we're going to dive into tests for circular data. So to begin, if you want to find out whether your data set is uniformly distributed around a circle or if it's clustered around one mean, you perform something called the Rayleigh test, and this assumes that your data set comes from a von Mises distribution. And the null hypothesis is that the data is uniformly distributed, and your alternative hypothesis is that the data is not uniformly distributed. You can perform the Rayleigh test in the CircStat toolbox using CircR test, where you're inputting your data set. Once again, you can see on the right, we have a data set of values. You can see from looking at the circle that it is clustered around a mean. The Rayleigh test from the CircStat toolbox picks this up. And if you test it, you get a p-value of 0.00. Therefore, the hypothesis is rejected, and we know that it is not clustered data. It's actually, sorry, it is clustered data. It's not uniformly distributed. All right, Columbus number 2.
So Nour presented you with the parametric test for uniformity. But what happens if your data, you cannot make the assumption that your data is taken from a von Mises distribution? One situation, for instance, is what happens if you have a multimodal distribution. The von Mises is unimodal. There's an equivalent. In fact, if you use a Rayleigh, it's going to give you the wrong, an incorrect result. We can see we have two distributions here. One on the left, which is arguably, we could argue whether it is uniform or not. In fact, it is a bimodal distribution with a very, in which the data are not clustered. There's a high variance. Okay, so this one could be, we could argue whether it's uniform or not. But the one on the right is obviously not uniform. It's made out of two modes which are directed in opposite direction, but those are two very sharp modes. And still the Rayleigh, the p-value is above 0.05, so in fact it's even higher than for the one on the left, and so the distribution on the right is considered to be, the Rayleigh test tells us that it misleads us into thinking that this distribution is uniform. So there are two non-parametric tests for uniformity. We present the results for both. But as it will become evident, we need to, using these tests, we need to understand how they work in order to understand their limitation. We're going to illustrate one limitation for the omnibus test. So we have two tests. The first one, the O test, is the omnibus test. The way it works is that it tries to find the 180 degrees, so the half circle in which you find the smallest number of data points, and what it does is that it compares the number of data in the circle, the half circle that has the less number, and the one that has the most. And intuitively, if we have a perfectly uniform distribution distributed around the circle, we should find in both half of the circle, we should find more or less the same number of samples. So if the two are significantly different, then it means that the distribution is not, it is an indication that the distribution is not uniformly distributed. The second test is the Rouse test. It tests the same hypothesis, but it employs a slightly different approach. So what it tests for the mean intersample interval. Intuitively, again, if we have a perfectly uniform distribution, and let's say we have 360 samples, what we would expect to find is that the mean interval between the samples would be 2 pi over 360. Simply because each sample will be evenly distributed. So that's the idea. So those are the two approach employed by each test. So the way you use, so these functions in bold characters are available in the statistical circular statistics toolbox. It's easy to use, so you just put in the data and you get out a p-value. It's that simple. Here's a few situations. So the distribution on top illustrates a distribution which is uniform. As you can see, both tests accepted the hypothesis and considered the distribution to be uniform. The distribution on the bottom is one in which there's an obvious polarization of the data towards northeast direction. Again, both tests picked that up and considered this distribution to be non-uniform. We have here, again, our bimodal distribution with opposite direction, the modes in opposite direction. This is a problematic situation for the omnibus test. If you recall, the omnibus test was trying to find the half circle with the less number of samples and compare it with the number of samples in fact, the half circle that has the most number of samples. If you look at this distribution, regardless of how you try to split the distribution in half using a diameter, you find that you always end up with the same number of samples on each side of the boundary. And but this distribution is not uniform, so the omnibus test is limited. And when we understand how the test works, we can see why it's limited. Honestly, from my experimentation, I would recommend that you use the Rouse test. In this case, the Rouse test did pick up the fact that this distribution was not uniform. The distribution on the bottom has 3 modes, so it's a 3-modal distribution, and both tests consider it as being non-uniform. So both tests work equivalently on this distribution. Back to you.
No, don't be sorry.
And we did practice. Can you believe that? Next time is 20 times.
All right, so what if you want to test not whether your data set is uniformly distributed around the circle or whether it's clustered around a mean, but if you want to see whether that cluster is actually equal to a mean direction. So to do that, we do a test for significance of the mean. This is analogous to the t-test for linear statistics. And the null, and again, it assumes that it comes from a von Mises distribution, so it's a parametric test. The null hypothesis is that the mean of the sample is not significantly different from the tested mean, and the alternative hypothesis is that the mean of the sample is significantly different from the tested mean. In the CircStat toolbox, you would use the function circmtest, where the first thing you enter is your data set of values, and the second one is the angle you want to compare your data set to. So on the right, you have a data set with an arose plot with a mean of 1.3828. If you were to first input a mean to test of 0, you would get a p-value of 0.00, highly significant, so your null hypothesis rejected, and we know that the data set you have is significantly different from 0. There we go. Whew. Okay. And if you were to test whether the mean you were testing is pi over 2, which is equal to 1.57, I believe, and you were to put this into the test, into the function, you would find a p-value of 1.00. So it's not significantly different. So the null hypothesis is accepted, meaning that the means are not significantly different, so they can be clustered together. I mean, they have the similar mean. Now, what if you don't want to compare your data to one specific mean, but you want to compute or see the difference or significance difference between two different distributions to see if they could be signified from two different populations or if they were part of the same population? You would use a Watson-Williams test. Again, it's assumed to come from a von Mises distribution. And the null hypothesis is that the two sample populations are not significantly different, so they can be clustered as one. And the alternative hypothesis is that the two sample populations are significantly different. So you would use the CircStat toolbox function circww test, and you can input your data in two ways. The second way is when you input two data sets so that are to be compared, or the first one on top is when you have one data set array and then you have the identifier to say which rows are being compared. And it outputs your p-values, your significance value, as well as a table of statistics if you ask for that output. So I'll give you two examples. So over here we have two distributions that both have a mean of 0, and if you put it into the test, the Watson-Williams test picks up on this, and you find a p-value of 0.987, which is not significant. Therefore, the hypothesis is accepted. So these two populations share a common mean and can be clustered together or put together. In our second example, we have two distributions. The one on the left has a mean of 0, and the one on the right has a mean of pi over 2. And if you put this into the Watson-Williams test, you find a p-value of high significance of 0.00, and the hypothesis is rejected. Therefore, these two populations are considered to be significantly different from one another. And that's all for me, folks.
So I'm actually dealing with for those who haven't noticed, I'm dealing with the non-parametric aspect of circular statistics. So Nour just presented you the parametric pair test to differentiate to test the mean. We have a non-parametric, the circular statistics propose an equivalent test, but it is a test on the median. I told you earlier that we were going to readdress the importance of the median. Why do we do tests on the median? So we decided to add a little extra to the talk, which can be extrapolated to other fields of statistics, not only circular statistics. So the posing question is simply, why do we test the mean? The median when it comes to non-parametric distributions. So this has to do with the notion of robust statistics. My claim is that a median is a more robust statistics than the mean is. Why is that? So to illustrate this, we have here 500 samples that are taken from a normal distribution, which has a mean of 0 and a variance of 1. That's the standard normal distribution. If we compute the mean, we compute the median, we find a mean of 0.07, a median of 0.07. This is fairly reasonable. The small deviation only has to do with the fact that this is a sample population. But what we're interested in is what happens if 10 of the samples, so it's only like, I didn't do the math, 10 out of, so it's 1 out of 10, it's 0.2%. Okay, so 0.2% of the data are corrupted by some, we can think of noise that comes, gets into a system. So only 10 samples are taken from a different distribution, which is centered on 10. So a normal distribution, same variance, but that is centered on a mean of 10. So here's what the distribution now looks like. So we have the same normal distribution on the left, but we now have 10 outliers. And outliers is really the term for that. If we're in a parametric environment, we can rule these samples out. No, we're allowed to do that as scientists, as statisticians. We can say these samples are outliers. I'm dropping these 10 samples, and then this solves the problem because we center ourselves on the normal distribution. But what happens when we're in a non-parametric environment is that, but first of all, this is an obvious case. Obviously, I mean, these outliers are very obvious. But when we're in a non-parametric environment, we don't have like a reference frame to tell which samples are outliers and which samples aren't. So we're kind of stuck a little bit. We have to take all the samples we have, and we have to do stats on them. So if, taking this distribution, if we compute again the mean and the median, what we find is that the mean is greatly affected by these 10 outliers. I remember this is only 0.2% of the data. And now the mean is now of 0.207, while the median is of 0.042. So both are affected, but notice how the mean is dragged much further away from the true mean that we said that was centered on 0 of the normal distribution. So because of that, the median, this leads to the conclusion that the median is a more robust statistic. That is, even if it's more resilient to outliers, and the median will be a better estimator for in this particular case. So this is the main reason why non-parametric tests will rely more on the median rather than the mean. So we have a function to, so we'll go back to our test, a non-parametric test, a non-parametric paired test on the median. So the question, the null hypothesis is that the two distributions have the same mean, the same median, while the hypothesis that is tested is if they don't have the same median. The function that the toolbox gives us is circ-CM test. The way you can call it is the same way as the ANOVA one in MATLAB. So you can either provide data and a group identifier, or you can provide two set of data. And what comes out is a p-value. You also have a median estimate. You see if the null hypothesis is not rejected, and also a set of statistics. The p is a structure that contains a set of statistics about the data. So a few examples. So here we have two uniform distribution. The p-value that comes out is 0.92. The thing here is that these two distributions are uniformly distributed. Therefore, the median itself is not significant. So the test simply tells us I cannot reject the null hypothesis. I cannot say that these two distributions don't have the same median, but it has mainly to do with the fact that the median itself is not significant. Still, in fact, if it was to tell us that the median are similar, this will be a problem. So that's what we expect in this situation. Here we have, here is to illustrate again the limitation of the test. So we have two distributions, and if you look carefully and you try to extrapolate, you will find that these two, the one on the left is bimodal. So it has two modes. I think one mode is pi over 4, and the other one is minus pi over 4. And the one on the right has only one mode, which is centered on a 0 rad. So these two distributions have, these two distributions have a very similar median. Okay, so the hypothesis is not rejected. The test cannot state that the medians for these two distributions is different. So what I want to illustrate here is that this test is not a test for disparity between the two distributions. It's a test on the median. So do not use it blindly, saying if they're different, it's two different distributions. The distributions can be different, and the test still cannot tell us that the median are different. We have here a situation for which, like, the test really applies almost the ideal situation. So we have two bimodal distribution. One is as a median, which is again pi over 4, and the other one as a median, which is minus pi over 4. They share a mode in common. The mode that's 0 rad is the same for the both, but the other distribution, in fact, to generate that, has some two von Mises distribution, and one mode is at pi over 2, and the other one is at minus pi over 2. And for these two distributions, the tests reject the hypothesis. These two medians are definitely different. Our last example. So we have, again, I bring back these three modal distributions. I can just say, I mean, I'm making some illustrations. If you really have to deal with three modal distributions, you have to work a little bit. You don't just apply, again, the test blindly. You have to look at data and everything, because not everything works perfectly in a trimodal or distribution. So, but these two distributions are, in fact, more or less of the same distributions, but one is rotated regarding the other. And what you find here is that the two medians are significantly different. So this is what the test said. Again, I'm going to be honest, the three modal distribution doesn't work fine. In fact, when you think of it, three modal distributions probably have three solutions for the mean that are more or less equivalent. So there's a little bit of a, but the two, anyway, for this one, the tests work fine. So this is, that's for the non-parametric paired test. Okay, so that's the end of our talk. So our point here is that we introduce a new field of statistics, circular statistics. I know I wasn't familiar with them like up to like last year. I think that, my supervisor, Chris Peck, said, "Oh, you should look into that." I personally use them to investigate the question of spike phase locking. So when you compare spikes and they're locking on a LFP phase. So these came out very handful to do that. I mean, this I know like there are some tools examples that they say for LFP and spike. What's the word? LFP spike. Not coherence, but correlation. I think, is it correlation? Yeah. I mean, it's similar. I mean, I know it's. I mean, I'm just saying what the tool is exactly, but it's similar. So you have stuff. If you also investigate the direction tuning of neurons, let's say you have a number of spikes and you see which direction, I mean, you should be using this kind of statistics. Before today, you didn't know that it existed, so you are allowed to make mistakes and not use the statistics. I mean, about statistics, there's always many ways to turn out the data and use different tools, but we hope that at least we sensibilize you that circular statistics first exists, second, that they're easy to use, and I think this can be a plus value. If you plan on publishing a paper and something, you show that you're using an appropriate, oh yeah, the planet. You're using an appropriate tool to analyze your data. So I think this is a plus value. So it's very easy. The circular stats toolbox, very well made, very intuitive. It works like along the way with other tools in MATLAB, and it comes with a manual. In fact, we base most of the talk on the paper that was published about the toolbox. I mean, you read the paper, it describes all the tests and everything, and then you just work a little bit. No, you add a little bit of stuff from Wiki, from other stuff, but no, you get a very good. The paper is very good. We cited it, yes, and this is we're gonna put it on the web and everything. So hope you enjoyed. Anything to say? Okay. So thank you. We're now open for questions. Yes, Greg. Significantly different from zero, yes. I think from my personal experience, I noticed that if the resultant vector is of length that is close to 0.3 or something, this is like where the switching between significant and not significant is if the length is greater than 0.3, usually you're significant. So this is why we presented like the variance and the resultant vector is that the test does statistics on these metrics. So this is really like what is accomplished by these tests, the Rayleigh test, namely. Yes, there is. We didn't talk about that. Yes.
Yeah. Yeah. For depending on the test you're using, but from what I remember reading, it has like a minimum of 5. Like.
Okay. Sorry, answer the questions.
But I don't like just to not give you any wrong information. Some tests do have limitations, and it is cited in the manual if you want to read it.
Yeah, that's right. We forgot to cover this matter, but yes, there's a. But I mean, but this is true from, yeah. No, it's not that much. I mean, statistics usually, I mean, I was given for like normal distribution, I think from 13, you start to have like significant statistics. Same thing should apply. I don't remember the exact number, but it's usually like around 10 and 15. And intuitively, if you have like less than 10 samples, I mean, what can you really say about your distribution? I mean, it's very hard to, and the thing also is that you have two factors affecting it. That is, if you have 10 samples that all fall on the 0 rad or very close to the very clustered, you reach significance much quicker than if your samples are like distributed like on half a circle. So you have these two factors. That is the number of samples, but also how clear is how apparent is the statistics given in your samples. Yeah. I know if you don't have, there's a number of samples that below which the statistics doesn't apply. Yes, there's. Yeah. 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 Next year we'll come back. Yeah. Any more questions? Okay. So thank you very much.